Outside, the Great Plains have disappeared. Snow moves horizontally. The temperature has dropped past the point where exposed skin begins to die within minutes, where breath freezes before it reaches the ground, where the open prairie becomes one of the most hostile surfaces on Earth. And somewhere in the middle of all of it, sheltered, warm, and alive, a family sleeps. No firewood, no furnace, no structure visible from the outside except a low, earthen mound half buried in drifts. How? The modern imagination, shaped by campfire movies and survival shows, defaults to a single answer when it pictures indigenous winter survival. A big fire, burning continuously, pushed against the cold. But for many Native American nations living across the treeless Great Plains, the frozen plateau, and the Arctic tundra, that answer was simply not available. Wood was scarce, buried under meters of snow, or entirely absent across hundreds of miles of open landscape. And yet these communities did not merely survive the coldest winters on the continent. They maintained warmth with precision and efficiency that modern thermal engineers have since studied and confirmed. The fire was only one small piece of a much larger system, and often it was the least important piece. To understand how, you have to stop thinking about warmth as something generated and start thinking about it as something protected. Among the Mandan, Hidatsa, and Pawnee peoples of the upper Missouri River Valley, the central winter structure was the Earth Lodge, a semi-subterranean dome anywhere from 30 to 60 feet across, built from heavy timber frames layered with willow branches, dried prairie grass, and finally a thick, continuous skin of dense sod and packed earth. From the outside, it looked like the land itself. From the inside, it operated like a precision thermal instrument. The physics were rooted in a single property of soil: thermal mass. Earth takes a long time to absorb heat, but once it does, it releases that heat slowly and steadily. During the brief hours of winter daylight, the thick earthen walls absorbed whatever solar energy the sun offered. As external temperatures collapsed at night, plummeting toward minus 40 degrees Celsius, those walls began radiating warmth inward, hours after the sun had set. The interior temperature remained stable not because a fire raged inside, but because the structure itself had become a battery charged by daylight. A central fire helped, but it was modest, not consuming. The semi-subterranean positioning added a second layer of insulation entirely independent of weather. Below the frost line, the Earth maintains a constant, stable temperature year-round. Cool in summer, but dramatically warmer than the frozen surface air in deep winter. By excavating several feet into the ground before building upward, the lodge bypassed the worst of winter at the floor level, where people lived, cooked, and slept. Ventilation required no mechanical system. The dome's low, hemispherical profile minimized the surface area exposed to wind, and less surface meant less heat lost to convection. At the very apex of the dome, a central smoke hole operated through fluid dynamics alone. High-velocity wind crossing the curved roof created a low-pressure zone above the opening, drawing smoke upward and out continuously without fans or flues. A long, tunnel-like entrance covered by a wooden screen prevented cold air from entering and disrupting the internal microclimate. Fresh air reached the central fire through precisely calibrated gaps, feeding the flame without flooding the room. Archaeological records confirm that a well-constructed earth lodge, even in severe weather, required only a small central fire to remain livably warm. The structure did most of the work itself. Across the northeastern woodlands, the Haudenosaunee took a different approach to the same problem. Their longhouses stretched up to 100 feet in length, with multiple families sharing a single elongated structure framed in heavy saplings and sheathed in thick bark. Rather than relying on a single hearth, fires were spaced at intervals down a central aisle. The heat circulated along the full length of the building, and the combined metabolic warmth of dozens of people living, sleeping, and cooking within a single enclosed space added meaningfully to the internal temperature. The longhouse was not just an architectural solution, it was a social one, turning communal living itself into a thermal strategy. For the nomadic nations of the open plains, the Lakota, Cheyenne, and Blackfeet, permanent earthen architecture was impossible. Their survival demanded shelter that could be dismantled, transported, and reassembled across hundreds of miles of frozen grassland. The tepee, which appears simple, was anything but. Modern thermal engineers who have studied tepee design consistently describe it as one of the most sophisticated portable shelters ever constructed. Its geometry was not a perfect cone, it was a calculated asymmetry. The base was oblong, the rear wall steeper than the front. The entire structure angled to lean slightly away from the prevailing western winds. When wind struck this tilted surface, aerodynamic forces pushed the structure downward into the earth, rather than pulling it upward. The tepee did not resist blizzards, it used them. But the defining thermal technology of the winter tepee was interior, invisible from outside. A hide liner called the dew cloth, suspended roughly 6 feet off the ground from the lodgepole frame. This inner wall created a continuous gap of dead air between the living space and the outer hide cover. Still air cannot conduct heat. It sits, it resists. The gap functioned identically to the vacuum layer in a modern thermos, trapping radiant heat on the inside and blocking the cold on the outside. The dual wall system also produced a controlled chimney effect. Cold air entering beneath the outer edge of the tepee was channeled upward through the gap, warming as it rose, drawing the smoke from the central hearth out through the apex. The living area remained warm and free of toxic smoke simultaneously. 2 adjustable flaps framing the smoke hole could be repositioned with exterior poles as wind direction shifted. A real-time flue managed from inside during a blizzard without opening the door. The Secwepemcs and Lakapamuks peoples of the plateau region built inward rather than up. Their pit houses were excavated directly into the hillside, roofed with a conical structure of heavy timber and pine needles, and then buried under the same earth that had been removed. A thick accumulation of winter snow on the roof amplified the insulation further. Archaeological evidence suggests these structures could maintain habitable temperatures in conditions reaching -42 degrees Celsius, using only a small fire, in some accounts barely more than coals. The entrance was a notched log descending through the smoke hole at the apex, the only opening in the entire structure. Cold air had no direct path inside. In regions where wet snow and rainfall were heavier, builders integrated layers of cedar bark into the roof, providing waterproofing without sacrificing the breathability the structure needed to vent internal moisture and smoke. But shelter alone did not solve the problem of the open prairie in winter. Fire still required fuel, and across hundreds of miles of treeless grassland, there was none. The Plains tribes solved this through one of the most practical ecological observations in the history of human survival. Bison, the dominant animal of the Great Plains, grazed almost exclusively on tough C4 grasses with extremely high fiber content. Processed through a ruminant digestive system and then desiccated by months of prairie wind and sun, the resulting dung was transformed into a dense matrix of dry cellulosic fiber. Bison chips, as they came to be known, burned slowly, produced consistent radiant heat and generated virtually no smoke. These properties made them, in several respects, superior to wood inside an enclosed dwelling. They did not fill a tepee or earth lodge with toxic fumes. They smoldered through the night without constant feeding. Euro-American pioneers crossing the same plains a generation later adopted bison chips immediately and wrote extensively about their effectiveness. The people who had been burning them for centuries already knew. When chips were buried under deep winter snow and inaccessible dried prairie grass, sagebrush, and rendered animal fat served as emergency backup fuels. Nothing was wasted, nothing was overlooked. Far to the north, in the absolute tree line of the Arctic, the Inuit confronted a different extreme. No wood, no bison, no prairie grass. The solution was a carved soapstone lamp called a kulik, a shallow, crescent-shaped vessel filled with cubes of seal, whale, or walrus blubber pressed to express their oil and fitted with a wick of Arctic cotton grass saturated in the fat. Once lit, the kulik burned steadily with a low, controlled flame. A single lamp heated an igloo, provided the only light during months of perpetual darkness, dried wet fur clothing, melted ice and snow into drinking water, and gently cooked raw meat. Tending the kulik was a specialized skill, managed primarily by women and requiring constant attention. Trimming the wick, balancing the oil flow, preventing soot buildup that would suffocate an unventilated snow structure. It was not passive maintenance. It was technical practice, refined over generations, and its failure could mean hypothermia within hours. The igloo itself exploited the one resource the Arctic provided in absolute abundance: snow. Compacted snow traps millions of microscopic air pockets within its crystalline structure. Those pockets prevent heat transfer. A properly constructed igloo, built from precisely cut blocks of compacted snow laid in a tightening spiral, could maintain interior temperatures 15 to 20 degrees Celsius above the external environment, using only the body heat of its occupants and the minimal output of a single kulik. The dome shape shed wind and ensured that any interior melting ran down the curved walls and refroze at the base, rather than dripping onto sleeping people. Where fuel was scarce, even by Arctic standards, archaeological evidence across Beringia and Siberia documents a further adaptation. Fractured, boiled animal bones could be burned. Bones from hoofed mammals, once their marrow had been extracted for soup and their lipids rendered by boiling, retained enough embedded fat to sustain combustion once the initial temperature was high enough to ignite it. A primer of dried grass or rendered fat started the process. The bones did the rest. This technology left zero waste from a harvested animal in an environment where every calorie of matter held potential value. Fire, once lit, was never carelessly extinguished. Embers were banked under thick layers of ash each night, the ash acting as a thermal blanket, starving the coals of excess oxygen, preserving them at high temperature for 12 hours or more without consuming additional fuel. Each morning, the coals were uncovered, exposed to air, and the fire resumed from where it had paused. Tribes that moved across the frozen prairie carried live coals in hollowed buffalo horns, packed with slow-burning fungi and sealed with a paste of sand and hide glue, with small air slits carved along the side to sustain the smolder. A new camp could be warmed immediately upon arrival, without the exhausting caloric cost of relighting fire from friction tools in sub-zero conditions. Hot stones extended the fire's reach further. Large river rocks heated in a central hearth were buried slightly beneath the dirt floor or positioned beneath sleeping areas, releasing radiant heat long after the fire died down. Water poured over these stones created steam, raising ambient temperature through the latent heat of vaporization, while simultaneously adding vital moisture to the dry winter air, protecting lungs and skin from the effects of prolonged cold exposure. This same principle, heating rocks with fire and using their stored energy for warmth and steam, also formed the mechanical foundation of the sweat lodge, a structure used in sacred ceremony across many nations, where the boundary between survival technology and spiritual practice was never clearly drawn. No system of shelter or fuel was complete without the body's own contribution to survival. Native American winter clothing was not merely warm, it was engineered to perform specific thermal functions. In Arctic and subarctic regions, caribou hide was the material of choice for a precise biological reason. Each individual caribou hair is hollow, a microscopic chamber of trapped air running the length of the shaft. The fur functioned as a dense matrix of dead air insulation worn directly against the body. Garments were constructed in 2 layers. The inner layer was worn fur side inward, trapping radiant body heat immediately upon emission. The outer layer was worn fur side outward, shedding wind and snow while preventing the inner warmth from escaping. The combination created an almost impenetrable thermal barrier with minimal weight, preserving the full range of movement required for hunting in dangerous conditions. For Great Basin tribes living where large game was scarce, the jackrabbit provided an alternative. Rabbit skin is warm but tears easily, making it unsuitable for conventional sewing. These tribes cut the pelts into long, continuous spiral strips, twisted each strip tightly so that fur faced outward along its entire length, then wove these fur-covered cords together on a wooden frame using a complex twining technique. The resulting blanket was structurally durable and thermally dense, a woven matrix of fur and trapped air capable of doubling as both clothing and insulated bedding. Where skin was directly exposed, across the face, hands, and neck, rendered animal fat was applied directly. Bear fat or goose grease created a hydrophobic barrier across the skin's surface, sealing in dermal warmth, blocking wind penetration, and preventing the cracking and moisture loss that accelerated frostbite. None of these technologies operated alone. Each one addressed a specific vulnerability in the human body's relationship with extreme cold, and each one depended on the others. The shelter reduced heat loss from convection and wind. The alternative fuel sustained the fire that moderated the internal temperature. The clothing maintained a personal microclimate against the skin. The diet fueled the body's own thermogenic capacity from within. Pemmican on the plains, a mixture of dried pulverized meat packed into dense cakes of rendered tallow, was designed to burn slowly in the body over hours, sustaining core temperature during blizzards that could trap families inside a tepee for days without resupply. In the Arctic, akutak, whipped animal fat emulsified with seal oil, fresh snow, and preserved summer berries, delivered massive concentrations of lipid energy alongside vitamin C, addressing simultaneously the body's need for warmth and its vulnerability to scurvy in the long, sunless months. Behavior completed the system. In the coldest nights, when the fire was banked and the structural insulation was doing its primary work, families did not sleep apart. Bodies were gathered under shared buffalo robes, combining their radiant heat into a single mass. Children, most vulnerable to heat loss because of their high surface area to body mass ratio, were placed at the center of these sleeping arrangements, flanked by adult bodies on every side. The group became a single thermal unit, each member's heat retained by all the others, each member's caloric expenditure reduced by the collective warmth. Bodies were also lifted off the frozen ground, using thick layers of dried grass and stacked hides, eliminating the direct conductive loss that would otherwise drain heat from below throughout the night. The cold was never fought directly. It was managed through every available variable simultaneously. Striking parallels to these systems emerge on the other side of the planet, developed entirely independently by peoples with no contact or shared language. The Sami of northern Scandinavia constructed a portable winter shelter called the lavu, a conical structure of spruce poles covered in reindeer hides, with a central hearth and an adjustable top opening for smoke management. Its thermal principles were functionally identical to the plains tepee. The Nenets of Siberia built the chum, an analogous conical structure, and burned dried reindeer dung when wood was unavailable, a fuel that performed almost identically to bison chips in composition and burn behavior. In extreme conditions, archaeological evidence confirms they burned fractured, boiled bones, mirroring documented Beringian Paleo-Indian practice across thousands of miles and an ocean of separation. The Nenets also wore layered reindeer hide garments constructed on the same dual-layer principle as Arctic North American clothing. Fur inward for warmth, fur outward for weather resistance. The hollow hair of the reindeer performing the same insulative function as the hollow hair of the caribou on the opposite side of the world. Identical problems, facing human beings with identical biological vulnerabilities, produced identical solutions. The tepee and the lavu were not cultural coincidences. They were the optimal engineering answer to a specific set of physical conditions, arrived at independently through careful observation and refinement over generations. That convergence is one of the most compelling things the archaeological record has to offer. Proof that human intelligence, pressed against the same wall by the same environment, finds the same door. What emerges from these survival systems is not a portrait of people struggling against a hostile world, but of people who understood their world with extraordinary precision. They knew the thermal behavior of soil and snow. They understood convection, insulation, and the physics of airflow through empirical practice refined across centuries. They read the caloric density of alternative fuels before the concept of calories existed. They engineered garments around the microscopic biology of hollow hair. They managed fire not as an infinite resource, but as a finite, precious one whose loss could kill, and whose preservation was a daily act of technical discipline. The coldest winters on the continent were survivable, not because of abundance, not because of brute force, but because of knowledge accumulated slowly, shared carefully, and applied with precision across every layer of daily life. The warmth was never in the fire. It was in the system built around it. And the system was the result of something no temperature could diminish. The relentless, adaptive intelligence of people who had learned, generation by generation, exactly how the world worked and exactly how to live within it.